Hello students, welcome to this lecture in which we continue talking about mass, and in this lecture we're going to talk about moments and center of mass. So we're going to suppose that the lamina occupies a region D, like in the previous lecture, a region D, and has a density function, rho of x and y. So the moment of a particle was defined in calculus 2, but let's restate it. So we can define the moment and we have a lot of physics major in our class, so they know what moment is. So the moment of a particle about an axis as a product of its mass and directed distance from the axis. So I took the picture from the last lecture. Sorry, some technical issues. One sec. So we had a couple of technical issues, but I took the picture from the last lecture over here. So this is our lamina in blue, and we occupy the region D over here. And what we do, we subdivide the region D into rectangles, right? So subdivide the region D into rectangles as in the picture. So what's next? Then the mass of each rectangle, the mass of Rij is approximately rho of x sub I star in x sub I sub j star y sub I sub j star times the area. So that means we can approximate the moment of r sub I sub j with respect to the x-axis, with respect to x-axis, maybe to the x-axis. So we take mass, we multiply by the distance, right? So that means we have rho of x sub I star x sub I sub j, y sub I sub j times delta A, which is an approximation of the mass, times the distance, right? And the distance from the x-axis to the point will be the y, I sub j star. So now we just need to add those things up. So now we add these quantities, and take the limit, like we always do. Take the limit as the number of rectangles becomes large. And we obtain the moment of the entire lamina about the x-axis. Alright, so it's the moment about the x-axis. So the moment about the x-axis as the limit when m and n go to infinity, so the number of subdivisions, so that means rectangles get smaller and smaller, and we take a double sum as I goes from 1 through m and j goes from 1 through n of y sub I sub j star times rho of x sub I sub j star y sub I sub j star times delta A. But basically this is just a definition of our double integral. So double integral over the region D, y times rho of xy dA. And the same way we get the moment with respect to the y-axis. So the same way we get the moment about the y-axis. Right, so we say my is the limit as m and n go to infinity the sum when I goes from 1 through m and the sum when j goes from 1 through n, x sub I sub j star, rho of x sub I sub j star, y sub I sub j star, delta A, which is equal to the double integral over the region D of x times the rho of x and y dA. And we define the center of mass. The center of mass, so that m times x, the center of mass, let's give it a name. Let's say center of mass would be at the point x bar, y bar, so that m times x bar equal to m y, and my bar is equal to mx. And the physical meaning is that the whole lamina behaves like let's put differently, as if its entire mass is located at its center of mass. Alright, so what does it mean physically? It means the lamina will be in balance when supported at its center of mass. So basically, if we have some lamina some lamina, and this is the center of mass over here, suppose it's here. This is our x bar, y bar. So if we put a support over here, some kind of a support, so it will be in balance, it will not fall down. Alright, so the last thing left is to figure out this x bar and y bar. So the coordinates x bar and y bar of the center of mass of a lamina occupying the region D and having density rho which is a function of x and y, r. So what would be x bar? X bar will be given by if we take the integral of x rho of xy, which is mx, which is my, and we divide by double integral over the region D of rho of xy dA, and in simple words this is just m sub y over little m. And we can say that y bar is pretty much the same thing, so double integral over the region dy times rho of xy dA divided by the double integral over the region D of rho of xy dA, which is just mx over little m. And little m is just the mass, right? and we defined it to be this denominator, right, rho of xy dA over the region D. All right, so we have our definition, so let's do an example. So our example is this one. Find the mass and the center of mass of a triangular lamina with vertices 0, 0, 1, 0, and 0, 2. If the density function rho of xy is equal to 1 plus 3y plus 3x plus y. All right, so let's build this triangle first. It says triangular lamina, so let's build the triangle. So first point is at the origin. Second point is 1, 0, so it's over here. And the last point is 0, 2. Let's move this point a little bit over here. So we have a triangle like this. All right, so this point is 0, 2, and this is 0, 0. So let's find the equation of this line first. So the slope will be 0 minus 2 divided by 1 minus 0, so it's negative 2. Then we have y-intercept at 2, so it's going to be y equals negative 2x plus 2. Right? mx plus b. Oh, mistake. mx plus b. And b is the y-intercept, which is this point over here. All right, so we know the equation of this line here is going to be negative 2x plus 2. All right, so let's find m first. So it's a slope. I'll put slope because I use m for the mass, so I cannot use m for the slope. All right, so what would be the mass m? Mass m will be equal to double integral over the region D of rho of xy dA. So integral, so our function is 1 plus 3x plus y dy dx. So let's see how our y changes for one particular x. So our y changes from 0 to this line, which is negative 2x plus 2. And our x changes from 0 to 1. So we go in, we integrate with respect to y. So we're going to get y plus 3xy plus y squared over 2, evaluated from 0 to negative 2x plus 2 dx. So now we're going to plug in the values. So we're going to get the integral from 0 to 1. So we have negative 2x plus 2 plus 3 times x negative 2x plus 2. Then we have plus negative 2x plus 2 squared over 2 And if we plug in 0, if we plug in zeros, everything will zero out, so we don't really need to do that. So we have this expression over here. Can we simplify it? Let's see. Let's see if we can simplify it. So we're going to get negative 2x plus 2 minus 6x squared plus 6x. Then we're going to square over here. So what we're going to get? So we're going to get 4x squared minus 2 times 2 times 2, which is 8x plus 4 divided by 2. So we divide, and so let's see what we're going to get. So we have we have 2x squared and negative 6x squared, so it's going to be negative 4x squared, so I counted for this term and for this term. Then we have negative 4x, negative 2x, so it's negative 6x and positive 6x. So this term, and this term goes away. And we have 2 and 2, so it's plus 4, evaluated from 0 to 1 dx. So finally we have negative 4x cubed over 3 plus 4x evaluated from 0 to 1. And if we plug in 0, everything will zero out. So we have negative 4 over 3 plus 4. And so it's going to be 3 times 4 is 12. 12 minus 8 is 12 minus 4 is 8. So we have 8 over 3 is our answer. So that was little m. This is our little m. So now we can set up our x bar, right? So our x bar is equal to 1 over m times the double integral over d Alright, so 1 over m double integral over the area d x rho of xy dA. So 1 over m, it's 1 over 8 over 3, and double integral becomes from 0 to 1, from 0 to minus 2x plus 2, and we have x times rho of x, which is x plus, so what was rho? Rho was 1 plus 3x plus y. 1 plus 3x plus y dy dx. So what do we get? We get a double integral 0 to 2 minus 2x plus 2 minus 2x plus 2, 0 to 1, and we get x plus 3x squared plus xy dy dx. So we get xy plus 3x squared y plus xy squared over 2 integral from 0 to 1, and this is evaluated from 0 to minus 2x plus 2 dx. And again, if we plug in 0, everything will zero out, so we just need to plug in negative 2x plus 2. So we're going to get x negative 2x plus 2 plus 3x squared negative 2x plus 2 plus x negative 2x plus 2 quantity squared over 2. Integral from 0 to 1 dx. So let's figure this out. So we have an integral from 0 to 1, negative 2x squared plus 2x minus 6x cubed plus 6x squared. Then we have x, 4x squared, 8x plus 4 over 2 dx. So, oh, I forgot. We have this term over here, which is 3 over 8. 3 over 8, 3 over 8, 3 over 8, and 3 over 8. So we have 3 over 8, 3 over 8, integral from 0 to 1. So let's try to simplify. So we divide by 2. Alright, so we have negative 2x squared plus 2x minus 6x cubed plus 6x squared plus 2x cubed over 2 is x cubed. 4x squared over 2 is, well, I already divide, sorry. I already divide by 2, so it's 2x cubed plus 4x squared plus 2x dx. So we have negative 2x squared, we have 4x squared here. And we have, this should be minus, right? This should be minus. Was minus, should be minus, and should be minus. Sorry about it. So this one, and this one adds up to 0. We have negative 6x cubed and 2x cubed, so this will be what? This will be will be negative 4x cubed. So I accounted for this term and this term, and we have 4x at the end. We have 4x at the end. Right, we have an integral from 0 to 1. We have 3 over 8 dx. So finally it's 3. We can factor 4 out. So it's 3 over 8 times 4, the integral of negative x cubed plus x dx. Alright, so we have 3 over 2 times negative x to the 4 over 4 plus x squared over 2 evaluated from 0 to 1. From 0 to 1. So if we plug in 0, everything will 0 out. So we plug in 1. 3 over 2, negative 1/4 plus 1/2. Right? 1/4 plus 1/2. And what is that? 1/4 plus 1/2 is 1/4. So we're going to get 3 over 8. The last thing left to find is y bar, which is 1 over m, the integral over the region D, y times rho of xy, dA. So we write it as 0 to 1. Here we have 3 over 8, the reciprocal of m, integral from 0 to negative 2x plus 2. And we multiply y by 1 plus 3 x plus y dy dx. Alright, so what do we get? We get 3 over 8, integral from 0 to 1, integral from 0 to negative 2x plus 2 of y plus 3xy plus y squared dy dx. So 3 over 8, then we do the antiderivative. We have y squared over 2 plus 3x y squared over 2 plus y cubed over 3 evaluated from 0 to negative 2x plus 2 dx. And this one is in parentheses. So we get integral from 0 to 1. If we plug in 0, everything will 0 out. Right, everything will 0 out, so that means no need to plug in 0. So if we plug in negative 2x plus 2, what do we get? So we're going to get negative 2x plus 2 quantity squared over 2 plus 3 over 2x negative 2x plus 2 squared plus negative 2x plus 2 cubed over 3, right, dx. So what is the easiest way to simplify here? Since we have negative 2x plus 2 squared everywhere, we probably factor it out, so we're going to get 4x squared minus 8x plus 4 if we square it and we put it outside. So we're left with 1/2 plus 3/2 x. So since it's just this term, and at the end we have negative 2x plus 2 over 3. Negative 2x plus 2 over 3 dx. Alright, so let's simplify this term first. So we have an integral, oh, I forgot 3/8 again. So it should be 3/8, should be 3/8, and should be 3/8. Alright, so let's try to add these three fractions together. Common denominator will be will be 6, right? Will be 6. Alright, so 6 is the common denominator, and we multiply this one by 3, so we get 3 plus 9x, 3 plus 9x, and over here we multiply by 2, so negative 4x minus, should be like this, so negative 4x plus 4. Alright, dx. And we can take 1/6 and we can put it outside. We can take 1/6 and put it outside probably. Yeah, alright, so if we put 1/6 outside, it's going to be 3 over 8 times 1/6 integral of integral of 3 plus 5x plus 4. Divided by, oh, we've factored 1/6 out, so this would be our function, so dx, right? but we also have 4x squared minus 8x plus 4. I forgot this term, sorry. So let me go back for a second and fix this up. Okay, one more try. Alright, so let's try to finish this one off. I didn't do it right the first time, so let's try one more time. So 3/8 integral from 0 to 1. So we have this term squared up front, which is 4x squared minus 8x plus 4. X squared, yeah. Then for this one, we would like to add those things up together. So we're gonna get, so common denominator is 6. Common denominator is 6, like we agreed before. So we put 6. So this one we multiply by 3, so we get 3 plus 9x. And this one we need to multiply by 2, right? So multiply by 2, so it's negative 4x plus 4 dx. And we took 1/6, we put it outside, and from this expression we can put 4 out. So 4/6 we put outside. 3/8, 0 to 1, so we put 4, we put 6. So this 4 is gone. We have x squared minus 2x plus 1. And over here we add up 3 and 4, so we're going to get 7 plus 5x dx. And then we're going to FOIL this out to simplify it. So 4 and 8 gives us 2, 6 and 3 gives us 3. Sorry, it gives us 2 here. So we get 1/4 integral from 0 to 1. We have 7x squared plus 5x cubed. So we're done with x squared minus 14x minus 10x. We're done with this one. It should be squared. And for 1, we have plus 7 plus 5x dx. All right. So what does it mean for us? That means we have integral from 0 to 1. We still have 1/4. So the highest term is 5x cubed. So this term is gone. 7x squared and negative 10x squared is negative 3x squared. So this term and this term is gone. We have negative 14x and we have 5x with a plus, so it's negative 9x plus 7 dx. So we did this term and this term, and this term over here is also accounted for. All right, so final step is we have 1/4, we have 5x to the 4, we have negative 3x cubed over 3 minus 9x squared over 2 plus 7x evaluated from 0 to 1. And since each term has x, if we plug in 0, everything will 0 out. So we plug in 1. So we have 5/4 minus 1, because 3 and 3 we can divide, minus 1/2 plus 7. Right, so common denominator is 4. So we have 1/4, 5 minus 4 minus 2 plus 14/4. And that's our almost an answer. So negative 6, so it's negative 1. Right. Forgot this -9. Forgot this -9, right? This should be 9, right? Should be 9, right? And should be times 2, so it should be -18. Okay, so what do we get? Alright, so we have this expression. I think I made a mistake over here with 14, should be 28, right? 47 times 4 should be 28. So we get positive 10 minus 4 plus 5, so it's 11. So we have 11 over 16. 11 over 16. So this is y bar. So we say the center of mass is at parenthesis 11 over 16 for y bar. This is x bar, y bar equal to, so 11 over 16 is for y bar, and for x bar we got for x bar we have what? This is x bar, 3 over 8. So basically if we put our support, it's 3 over 8 and 11/16, then it will be in balance. So if we take our picture, maybe we'll draw a new one to finish this lecture. So our original picture is, so we go 2 units up and 1 unit to the right, so we have this picture. So this is 1 0, 1 and 0. This is 0 2, and this is 0 0. So if I go to 3 8s, 3 8s and 11/16, 3 8s and 11/16 on the y-axis. 3 8 is just a little bit smaller than a half, so my picture is a little bit off. So here, 3 8s and 11/16. Over here, right? That's our x bar, y bar. 3 8s and 11/16. All right, so that concludes this long lecture with a lot of calculations. And next time we move to the vector fields. See you next lecture.